This is question 5 from the British Mathematical Olympiad, Round 1, 2001. We are required to prove this statement, that a squared plus b squared plus c squared equals 8r squared mutually implies that ABC is a right-angled triangle, where r is the radius of the circumscribing circle of the triangle. And by the sine rule, a over sin A is b over sin B, which is c over sin C. We're going to do the easy bit first and prove that if ABC is right-angled, then that sum, a squared plus b squared plus c squared equals 8r squared, holds. So we suppose that the right angle is BCA. This means that sin C equals 1. And from the sine rule, we know that b equals 2r sin B. And we know that a equals 2r sin A. And so C equals 2r, because sin C is sin 90, which is 1. And so a squared plus b squared plus c squared here is going to be the same as 2r sin A squared, because that is A, 2r sin B squared, because that is B squared, and 2r squared, because that is C squared. And because C is 90 degrees, the angle A plus angle B equals 90 degrees, and sin A equals cos B. So this here becomes 4r squared sin squared A. This becomes 4r squared cos squared A, because sin A equals cos B, and cos A equals sin B. And then we have plus 4r squared from there. And that becomes 4r squared times sin squared A plus cos squared A plus 4r squared. The Pythagorean identity, this is 1. And so we have 4r squared plus 4r squared, which is 8r squared. And that is the required result in the case where we know the triangle to be right-angled. We now come to proving the other statement, that if a squared plus b squared plus c squared equals 8 big R squared, then the triangle is right-angled. Now, from the sine rule and its relationship with 2r, we know that a squared plus b squared plus c squared equals 2r sin A all squared plus 2r sin B all squared plus 2r cos C all squared. And so we're required to prove that 4r squared times sin squared A plus sin squared B plus sin squared C equals 8r squared implies that ABC has a right angle. Now we have to bear in mind here that sin C equals sin A plus B, which is sin A cos B plus sin B cos A. And so it will simplify matters if we simply write this out again, but with C having been replaced by A plus B, and do the necessary squaring, and divide both sides by 4r squared. And so what I have done here, I have replaced sin squared A with the square of sin A plus B. I've divided both sides by 4r squared to obtain 2 here. And my instinct is to relate equations to 0 So instead of sin squared a, I have 1 minus cos squared a. Instead of sin squared b, 1 minus cos squared b. And that gives me 1 plus 1 equals 2, which I can subtract off the left-hand side. And so by the time I get down here, I have related the equation to 0. And if we look there, we will see that what this comes to is minus 2 cos squared a cos squared b plus 2 sin a sin b cos a cos b, and therefore this factorization here is possible, and that leads to the key result that either cos a cos b equals 0, or sin a sin b minus cos a cos b is 0. So that if cos a cos b equals 0, cos a or cos b equals 0. In which case a or b equals 90 degrees, and we have our right-angled triangle. But on the other hand, if neither cos A nor cos B is 0, then the alternative is that sin A sin B minus cos A cos B equals 0. Therefore, sin A sin B will be equal to cos A cos B, and I can divide both sides here by cos A cos B. And I've got sin A sin B over cos A cos B will therefore equal 1, which will be the same as tan A tan B, if you look here. There it is. And if 1 equals tan A tan B, A plus B must be 90 degrees, and therefore C must be 90 degrees, because the tangent of A is 1 over the tangent of 90 minus A. And I have now completed the proof.